Section 7.2, Hypothesis Testing for the Mean with the Standard Deviation known. Our last section we talked about hypothesis testing. We're going to put it to practical use today. When we look at a p-value, we're going to compare our p-value to our alpha. Our alpha is what I call our make or break. Let's suppose my p-value, and that really is what a z-score is 0.0237. Now, if I'm given an alpha of 0.05, what I have here is, you can see under here is from the very beginning of this curve, it's left tail, by the way, it's on the left side, the 0.05. Here is 0.237 right here. Then here's 0.01. When I look at this, if my number falls, my 0.0237 falls outside of the 0.05. It's on the outside. Again, here's my 0.05 right here. Here's my 0.237 right here. It's on the outside of it, so I'll reject it. But what if I got 0.0237 as before, but my alpha is 0.01? Well, now it's on the inside, so I would fail to reject it. What if I have a p-value of a hypothesis of 0.0745? What's my decision whether I accept or reject this? Remember, p has to be greater than alpha. Now, at 0.0745, it is greater than my alpha 0.05. It's closer to the mean. And if you look at this, that is 7%, 7.45% of the curve. And if my alpha is 0.05%, well, it falls within that. So I would fail to reject it. I'd accept it, but we say fail to reject. But if it's 0.10 is my alpha right here, alpha 0.10 is to the right of this. And here's 0.0745. It's on the outside. 0.0745 is here. 0.10 is here. So I would reject it. Now we'll put some practical use here. What I have here is I got a bell curve. And I'm going to look at this. I actually got the sheet right here for less than 50%, negative z-scores. Find the p-value for a left tail hypothesis statistic with a standardized test statistic of z equals negative 2.23. Decide whether to reject H of O when the lowest significance is 0.01. All right, my z of negative 2.23. Let's look at what 2.23 is. Here's negative 2.2. Here is 0.03. And that is 0.0129. 1.29% of the curve. Now I've drawn this bell curve right here. It's right here. This little red line right there. And if alpha is 0.01, it's within the acceptance part. I'd fail to reject it. If it was outside of it, it's on this side of my 0.01, I'd reject it. But it's on the inside of it. It's right here. So I'd fail to reject it. Let's look at another example. Find a p-value for a left tail hypothesis test. And we see it's on the left side of the curve with a standardized test statistic of z equals negative 1.71. Decide whether to reject the null hypothesis when the level is 0.05. I've drawn a curve here, a bell curve. And as you can see, my acceptance rate is 0.05. And this longer line is always the very beginning of the curve. So the 0.05 is actually right there. And this is 5% of the curve, this blue underneath. Now, when I look at z point negative 1.71, there's negative 1.7, and here is 0.01. That ends up being 0.0436. 0.0436 is where this red line is. It's on the outside of 0.05. It's 4.36%, but this is 5%. So we'd reject it. It's on the outside. Now I've got two tail hypothesis tests here, and I really don't need both sheets. I just need one side of it. In fact, I can just use the negative side in many cases because I'm looking for the space outside. Remember, everything under the curve is 100%, but I want you to pay close attention to this. A standardized test statistic of 2.14. Let's see what 2.14 is. It's actually going to be negative 2.14. And decide if actionable is the level of significance of 0.05. It's two-tailed. So it's 0.05 on two sides combined. So it's 0.025 here and 0.025 here. It's two-tailed. Again, it's two-tailed, which means 0.05 divided evenly. Now, alpha is 0.05 here. That's our significance level. And I split it up in two ways. If P is greater than or equal to alpha, we'd fail to reject it. We'd accept it. And there's our equality statement right there. Well, let's look at what 2.14 is. Negative 2.14 is right here. And there's negative 2.14 right there, which gives me 0.0162. 0.0162 is outside the 0.025. Everything in this blue here is anything I'll accept. Outside of that, I'd fail to reject. Outside of that, I reject it. 0.0162 is outside of 0.025 on both sides. So I would reject the hypothesis where P equals 0.0162. And again, if I use the positive side, it'd actually be 0.983 because this 1, this is 0 right here at the very beginning. This is 100% or 1. And it is on this side 0.0162. And on this side, it's 0.0162. But I could look on the sheet and say this is 100 or 1, 100% or 1. 1 minus 0.0162 is 0.9838. Remember, this is symmetrical. You're on a two-tail hypothesis test. A standardized test statistic of 1.64. Z equals 1.64. Now it's two-tailed, so that means I'm going to split up both two ways. And if I look at Z at negative 1.64, and B plus 1.64 is the same thing, again, because it's symmetrical. Negative 1.64 is 0.0505. And we want level of significance at 0.1. And that would be, since it's two-tailed, it'd be 0.05 on the left side and 0.05 on the right side. And when I look this up here, I got 0.0505. It is within the fail to reject. It's in the acceptance area. Barely. Anything out here, I'd reject on this side. Anything out here, 0.05, I reject. But it's within that. Just barely. But so I'd fail to reject. Now, we can use a z-test also. We got to make sure our sample is 30 or that it is a normal distribution. We state the null and alternate hypothesis. And remember, null hypothesis has the equality statement. Equal to, greater than equal to, less than or equal to. An alternate hypothesis has the less than or greater than or not equal to. We use our standard test statistic as before using the last chapter. Remember, my z-score is my sample average, my individual sample I'm looking at, minus my mean over the deviation divided by the square number of samples. And again, a left-tailed test, that means that acceptance and rejection region on the left side. Right-tailed test, it's on the right side. Two-tailed is split down the middle. We have to go 50% on both sides of it. If P is greater than or less than or equal to A, we reject it. Or if P is greater than A, we'd fail to reject it. It depends on what we're doing here. So let's look at some examples. NASCAR racing. In auto racing, a pit stop is where a racing crew stops for new tires, fuel repairs, and other mechanical adjustments. The efficiency of the pit crew makes these adjustments can affect the outcome of the race. Pit crew claims it has mean time for changing 4 new tires and adding fuel is less than 13 seconds. So before I go any farther, I'm going to do my null and alternate hypothesis. They are claiming it's less than 13 seconds. And that's an inequality statement. Now, they're trying to make the claim. So the alternate hypothesis is U is less than 13. That's where the claim's going to be. If that is the inequality statement, then what we're testing for the null hypothesis, it's greater than or equal to 13. Claim can go on either side. They'd like to prove it's less than 13. So let's set up our z-score here. Now we know our sigma is 0.19. They give it to us. I should finish reading this. A random sample 32 pit stop times has a sample mean 12.9 seconds. So the population mean of 0.19 seconds. Is there enough evidence to support the claim at alpha 0.01? A lot of numbers here, but let's sort them out. All right. That should be not population mean, population deviation. So my deviation is 0.19 seconds. My population mean is 13 seconds. My sample mean, they said they're doing 12.9 seconds. And how many have they've done with? They've done 32 samples right down here. And I know it's left-tailed because we're the alternate hypothesis that arrow's pointing towards the left. That's how I know it's left-tailed. So let's plug these numbers in. My sample mean is 12.9 seconds right here. My population mean is 13. So that's minus 0.01. My deviation is 0.19 right here, divided by the square root of 32, which is 5.66. So negative 0.1 divided by 0.19 divided by 5.66 equals negative 2.98. So my z-score is negative 2.98. Now let's look up what that is. What percentage is that under the curve? Here's negative 2.9. Let's find 8 here, 0.08. So negative 2.98 is 0.0014. So at 0.0014, and we're talking about an alpha at 0.01. Here's my alpha 0.01 here. That's 1% of the curve. 0.0014 is less than 0.01. So we would reject the null hypothesis, which means we're rejecting this one right here. It's greater than or equal to 13. We're actually saying we support the claim on the alternate hypothesis. Alternate does not mean it's bad. It means we want it to be less than 13 seconds. In this case, they proved this statistically. Here's another one. Homeowners claim that the mean speed of automobiles traveling on their street is greater than the speed limit, 35 miles per hour. Sounds like some person does not like people speeding in their subdivision. A random sample of 100 automobiles has a mean speed of 36 miles per hour. So they're saying it's greater than 35, and they did a sample, and they found out the average speed of 100 cars in this sample is 36 miles per hour. Assume the deviation population speed is 4 miles per hour. Is there enough evidence to support the claim at alpha 0.05? So let's look at this. We know our standard deviation is 4 miles per hour. There's our sigma. Our population mean is 35 miles an hour. Our sample mean of those 100 cars is 36 miles an hour. And we want to know the alpha at 0.05. So when I look at it, how do I know what the null or hypothesis is? Homeowners claim that the mean speed is greater than. There it is, literally right there. So it's not an equality statement, it's an inequality, which means it's going to be the alternate hypothesis. And that's where the claim is. They're making the claim on the alternate, that the mean speed is greater than 35, which means the null has to be less than or equal to 35. So let's test this out. Let's plug this in. My sample mean is 36. My population is 35. 36 minus 35 is 1. My deviation is 4, divided by the number of samples, which is square root of 100, which is 10. So it's 1 over 4 over 10, which is 2.5. So my z-score is 2.5. And let's look up, and I got the positive side here. So 2.5, that's 2.50. So it'll be right here. And 2.50 is 0.9938. Now, that means from the very beginning to this point right here is I should say this point right here, the little red mark up there, is 0.9938. 99.38%. And subtract that from 1, that means this remaining amount here is 0.062. So now I got 0.05. 0.0062. Remember, we're going from the outside here. Is less than 0.05. So we reject it. And that supports the claim. Since we're rejecting the null hypothesis, it supports the claim they are going faster than 35 miles per hour. Here's another one here. According to a study of U.S. homes at heating equipment, the mean temperature at night during the winter is 68.3 degrees Fahrenheit. You think this information is correct? Now, before we go any farther, whenever you see something like it's incorrect, it's not saying it's greater than or less than. It either is or it isn't. So I like writing the null and alternate hypothesis first. It says incorrect, 68.3. So that means the null hypothesis, that alternate hypothesis is where the claim is because you think it's incorrect. U is not equal to 68.3, which means the null has to be the equivalency statement, which is U equals 68.3. So you're going to select 25 homes, find that the mean indoor temperature is 67.2. For past studies, the population deviation is under 3.5 degrees, and it's normally distributed. And the reason it's not normally distributed is less than 30, 25. But if they tell us normally distributed, we can assume a normal distribution in terms of our calculation. So we want to see if there's evidence to support the claim at alpha 0.05. Use the p-value. So we got deviation of 3.5 degrees. Our population mean is 68.3. That's one we think is incorrect. The sample mean is 25 homes, 67.2. So I'm going to do 67.2. My sample mean minus my population means 68.3, which is negative 1.1. In my denominator, I got a population deviation 3.5 divided by 25. So 25 homes, which is 5. So negative 1.1 over 3.5 over 5 equals negative 1.57. Let's see what negative 1.57 is. There's negative 1.5 right there. and here is 0.07. So negative 1.57 is 0.0582, 5.82%. But it's two-tailed because I have an equal or not equal. Never have an equal or not equal. That is a two-tail. So 2 times 0.0582 is a total 11.64. We want to know alpha 0.05. Alpha 0.05 is 0.025 on both sides. So what I have here is I have 11.64. This is where my study falls, these 25 homes. It's between 11.1164 on the left, 0.1164 on the right, and my acceptance range 0.025. So we would fail to reject the null hypothesis. We're saying it passes null hypothesis, and we cannot right here. It doesn't change. So it does not support our claim. Now, so this one here, a lot here. I want to make sure we get this correct. According to a study of employed U.S. adults age 18 and over, the mean number of workdays missed due to injury or illness in the last 12 months is 3.5 days. That is going to be my population mean. You select 25 employees age 18 and over, same kind of group, and find the mean number of work days is missed is 4. So that's your sample mean. Assume a population deviation 1.5 days. There's my sigma. The standard deviation, and the population normally distributed. And again, we're saying normally distributed because there's less than 30. Is there enough evidence to doubt the claim at alpha 0.01? Use the p-value. Let's look at this here. We want to know, you're going to select 25 more days. We're doubting the study's claim. We didn't say it's greater than or less than. You're saying you don't believe it, which means you don't think it's 3.5 days. And unless you hear the word greater or less than or at least or at the most, if you have to assume it's a not equal and you're making the claim to doubt it, so that's the alternate hypothesis, not equal to 3.5, which means the null has to be the equivalency statement, which is 3.5. Let's plug it in our formula. Population, sample mean, which we got 4, minus population mean, 3.5 is 0.5. My denominator, I got a deviation of 1.5 divided by square root of 25, which is 25 individuals sampled. So it's 0.5 divided by 1.5 over 5, which is 1.67. Now 1.67, take a look at this. And I'm using the negative side, but it's the same thing on both sides because we're going down the middle here. There's negative 1.6. There is 0.07. This says here it's 0.475. So 0.475 on this side and 0.475 on this side. And alpha, if I add those up, that'd be 0.09. And alpha is 0.01 here, two-tailed. So we would fail to reject the null hypothesis, or we'd accept it because we're showing our sample falls within the acceptance region right here. Would have fallen outside the 0.01, I should say, put here actually from here, sorry, from here out, or from here out, we would reject it. But we fail to reject it because it falls within the realm of the failing to reject. Now, up in the last chapter, we were talking about everything within it. When we were rejection regions, that's on the outside. It's still 100% of the curve. And when I'm looking at this, let's look at this curve in the lower right here. This is 0.01, which is 2.33 Z's. 0.01, that's 1%. which means the remaining space under this curve, all the way to the very beginning, or the very end, I should say, is 0.99 or 99%. And anything outside of this, that's left-tailed, we'd reject. Anything greater than this, we'd fail to reject or we'd accept. And if I had a 0.01 is negative 2.33. So if I had a 0.005, I'd reject it. 0.009, anything less than 0.01. If I had 0.2, 0.3, 0.8, anything greater than 0.01, even 0.02, or even 0.011, I would fail to reject it. I'd accept it. Now let's look at this one here. Find the critical value in rejection region for left-tailed test with alpha 0.01. Okay, alpha 0.01 is 10% of the curve, is left-tailed, so I'd go from, here's 10% under the curve, right here, which means the other 90% or 0.9 is right here. And when I look at 0.10, we're doing the reverse here. We're going to find the z-score. When I look at this, I'm looking for the number that's closest. There is, let's see here. This one, 0.1003, is negative 1.28. See, the next higher one is 0.1020 right there, and that other one is 0.095. This is the closest 10% or 0.10. So I'm going to say negative 1.28, and there's my z-score. We're just going to reverse what we're doing. And anything with a z-score of less than 1.28, I'd reject. Anything greater than a z-score of negative 1.28, I'd fail to reject. Now let's see, this is two-tailed here, alpha 0.05. And remember, it's 100% under the tail. If it's two-tailed, 0.05, that means half of it, 0.025, is on the left side, half of it's on the right side. And at 0.05, that means the remaining part between this is 0.95. And everything under the curve is always 100% or 1. So 0.025 plus 0.95 plus 0.025 is 1. Now, this is going down the middle here, so we have to be careful. This is 0.95 down the middle. So I want to know what z-score it is. And the best way to find this, as we did before, I just got to find one side. It's symmetrical. So if I find one side, I can find the other. I know from here to this, from the very beginning to 0, is 0.5. And this is 0.95 all the way across in this blue part, which means it's half of that on each side, symmetrical. 0.475 on the left and 0.475 on the right. So I've gone to the very beginning. I would just point to the median, to my zero deviations, which is 0.5, plus to this point right here, which is 0.475. And 0.5 plus 0.475 is 0.975 right here. Now, I could also go this way. Look up on the sheet, and that's how I've got the sheet right here. I know this is 0.475, so I could go from here to here is 0.5 minus this part, which is 0.475, which equals 0.025. So I'm going to see what 0.025 gives me for a score. And remember, if I can find one side, I just find the opposite number to get the other side, the positive. So let's see 0.025. 0.025 in terms of space, 2.5%. And it is, perfect number right here. There it is. There's 0.0250, which is negative 1.9 So right here, and I've written it right here, my z-score for two-tailed, my lower end is negative 1.96. It's symmetrical. So my upper end is plus 1.96. And we can use a sheet and find out 0.5 plus 0.475 is 0.975, which is also plus 1.96. Let's see this one here. Find the critical values rejection region for two-tailed test at alpha 0.08. Alpha 0.08, it's two-tailed, tells us two-tailed, which means it's 0.04 on each side. And I'm just going to find the left side here. So this is 0.04. All the way across is 0.5. So I'm going to subtract 0.04 from my 0.05, 0.50, and that'll give me this far right here. Now, actually, I don't need to do that. I just realized I just need to go from the very beginning to 0.04. So let's look up where 0.04 is. And the closest is here's 0.0401. Next higher one's 0.0409. That's higher than this. This is 0.392. That's lower than. So 0.0401 is the closest, and that gives me negative 1.75. So my left score is negative 1.75, and my right score is plus 1.75. So anything that's less than negative 1.75, I'd reject. Anything greater than plus 1.75, I also reject. And this blue part in the middle is the fail to reject, the acceptance region. Now, we can do the same thing with the z-test using the z-score. Let's go through this. Have to still state our null hypothesis, find the z, use the z-table, and find our test statistic, and then determine if we reject or fail to reject. Employees at a construction and mining company claim that the mean salary for a company's mechanical engineers is less than its competitors. So the employees aren't happy with the boss. And they claim, they said for the competitors, it's 88.2. They do a random sample of the company's engineers, find out it's 85.9. Assume the population standard deviation of 9,500, and it's normally distributed because there's only 20, but there's nothing normally distributed. Alpha 0.05, let's test the employee's claim. So my alpha is 0.05, and let's see what they're saying. It's very known on our hypothesis. It's less than the competitors. So if it's 88.2, they're making the claim it's less than, there's my less than number. And since it's less than, it's pointing to the left, it is left-tailed. And since it's less than for the alternate hypothesis, that's what I'm making a claim. The null hypothesis is the equality statement. It's greater than or equal to 88.2. Now, let's see what alpha 0.05 is. And I think we already found that a little while ago. There it is. No, we didn't. It's negative 1.6, but perfectly between 0.04 and 0.05 right here. 0.0505, 0.0495. So we put 1.645, negative 1.645, this is left tail. And that's what I've written here. So we got to figure out what our z-score is with the sample of the 20 engineers, and then subtract the population mean, which is 88.2. So 85.9 minus 88.2, which is minus 2,300, divided by the deviations, 9,500, divided by the square root of the number of samples, is 20. And that's negative 2,300 over 2.21426. It's 2,214.26. I get negative 1.08. So my z-score is negative 1.08. 1.08, negative 1.08 is right here in this dotted line. This is the rejection region right here. This is the fail to reject. So we would fail to reject the null hypothesis, which means we can't support the claim. They're saying the salary is similar enough. It's not less than 88.2 statistically. So the salaries are roughly the same. Now, sounds like the CEO wants to get even with these employees. CEO of the above company claims that the mean workday of the company's mechanical engineers is less than 8.5 hours. This boss has ran a sample of 25 company's mechanical engineers, and they have a mean workday of 8.2 hours, assuming a population of 0.5 hours. And the CEO wants to see at alpha 0.01 test the CEO's claim. And the CEO says it's less than 8.5 hours. So let's do our hypothesis writing. Here's less than 8.5 hours. It's an inequivalent. It's less than. So that is the alternate hypothesis. Null hypothesis has the equivalency claim, which is greater than or equal to. And right here, it's left-tailed because the arrow is pointing to the left. Alpha 0.01 gives me a z-score of negative 2.33. Let's make sure. Here is this right here, 0.0099 is the closest to 0.01. So it's negative 2.33. So that's 0.01. And then now let's see what the z-score is for this sample. The sample work hours, he did 20 employees, 8.2 minus 8.5. The population is negative 0.3. Deviation is 0.5 divided by the number of samples, which is 25. Where 25 is 5. So it's negative 0.3 over 0.1 is negative 3.00. Z is negative 3.00. Our make or break region, our alpha, is negative 2.33. Negative 3.00 is less than. It's in the rejection region. So we're rejecting the null hypothesis. And that means it supports the claim they are working less than 8.5 hours. Researcher claims that the mean cost of raising a child age 2 and under by a married couple is $14,050. In a random sample of married couple families in the U.S., the mean cost of raising a child is $13,795. The sample consists of 500 children. Assume the population deviation of $2,075 and alpha equals 0.1. Is there enough evidence to reject the claim? And it's not telling me it's greater than or less than. He did a study, or she did a study, and his researcher said it's different. So which means it's equal or not equal. They're saying it's 14,500 population mean. So my null hypothesis is going to be equals 14.050. Which means the null where he's claiming is not equal to that. It's just not equal. It's not equal to 14.050. Alpha 0.10, it's going to be two-tailed. So it is because it's equal or not equal. So since it's two-tailed, I split that 0.10 in half and 0.05. And let's just find the 0.05 on the left side. 0.05 is going to be, I think we just found this a while ago, right here again. It's between 0.0505 and 0.0495, between 0.04 and 0.05. So it's negative 1.645. So it's negative 1.645 on the left, positive 1.645 on the right, and this is our fail to reject region. It's got to fall within that to support the null hypothesis. Put our numbers in. 13,795 is the sample of this person of 500 children. Population means 14,050. 13,795 minus 14,050 is negative 255. Divide by the population deviation, 2875. And that's divided by the square root number of samples, 500. And it ends up being negative 255 over 128.57, which is negative 1.98. The z-score is negative 1.98. And that is 1.64. Anything less than 1.645, I'd reject. Anything greater than plus 1.645, I reject. Those are the rejection regions. So this is in the rejection region, that negative 1.98, because it's less than negative 1.645. So we would reject the null hypothesis that's equal to 14,050 dollars, and we would support the claim. Now, same information as before, but instead of 0.05, it'd be 0.01. And 0.01 is 0.005 on each side, still two-tailed. And let's see what 0.005 is. It's a real tiny number here. I'm going to look on the table here. It looks like it is, let's see. Yeah, it's the closest this is right here. Between these two, 0.0051, 0.0049. Fall right between that. So it'd be negative 2.578. So negative 2.575 right in the middle. So it's two-tailed. So it'd be negative 2.575 on the left side, plus 2.75 on the right side. Anything below negative 2.575, I'd reject. Anything greater than plus 2.575, reject. Anything greater than negative 2.575 and plus 2.575, I'd fail to reject. I'd accept it. And when I put my numbers in here, I got 1.98 as I did before. Well, negative 1.98 deviations is greater than negative 2.575 and less than plus 2.575. So we would fail to reject the null hypothesis. So 0.01, we can accept the null hypothesis.